Hello, I'm Yunso from Dongguk University DTM Lab. Today I'll be presenting a paper review on the topic exploring potential R&D collaboration partners using embedding a patent graph. First, here is the bibliographic information of the paper. This study was published in 2023 in the Sustainability Journal. The following are the keywords in this study. The presentation follows the same structure as the paper. Companies need strategies to quickly discover new collaboration opportunities. Identify potential R&D collaboration partners is related to organizational innovation. In addition, collaboration between organizations is important for knowledge diffusion. Patents are used to find opportunities for technological innovation. In particular, co-patents are used to identify potential collaboration partners. Co-applicants can demonstrate their technological potential through R&D collaboration. This study aims to identify potential R&D collaboration partners using patents that have co-applicants. To do this, co-applicants are extracted and transformed into a graph, and then embedding is applied. Next, potential R&D collaboration partners are identified using a similarity-based relevance algorithm. The research questions are whether co-applicant information can explain business opportunities and whether it can be used to identify potential R&D collaboration partners. Previous studies have proposed methods to identify R&D collaboration partners, but they have limitations. Business opportunity identification based on patent maps does not fully reflect the characteristics of organizations. Knowledge graphs are important for understanding collaboration, but studies based on patent topic or IP code have the limitation of relying on technology keywords. Therefore, this study used co-applicant graph embedding and a similarity-based relevance algorithm. Graphs are stable for representing relationships between data, and they consist of nodes and edges. Recently, representation learning techniques for unstructured data have developed, and there have been attempts to apply them to graphs. Representative methods include skipgram-based debug and node-to-vec. Through this method, nodes can be embedded into a vector space. In a knowledge graph, rings describe the relationships between nodes. Ring prediction is the task of predicting whether an edge exists between a pair of nodes. Early link prediction was performed in a simple way based on structure similarity. However, this approach cannot reflect complex relationship structures. Therefore, more recent methods use node embedding. Through a node embedding function, each node is converted into a vector, and a prediction model is used to classify whether a link exists. This study aims to identify potential co-applicants in order to explore new business opportunities. First, co-applicants are extracted from patents and transformed into a knowledge graph. Next, applicant sequences are extracted and trained based on skipgram to perform node embedding. Finally, MMR is used to identify potential R&D collaboration partners in the vector space. Skipgram and node-to-vec are embedding methods that map nodes into a vector space. Previous studies have shown that network node and natural language node follow a similar power law distribution. Figure 2a shows that the news dataset follows a power law distribution. It was also analyzed whether patent applicants follow a power law distribution. and the result is shown in figure 2b. The autonomous driving pattern data used in this study also shows the same pattern as shown in figure 2c. Therefore, it is reasonable to apply natural language-based embedding methods such as skipgram and node-to-back to the co-applicant graph. In this step, a knowledge graph is built with co-applicants as nodes, and the co-applicant nodes are converted into vectors. In the co-applicant graph, the neighbors of a specific node are likely to be co-applicants. By running this structure, collaboration relationships are mapped into the vector space. At this time, the model is trained so that the distance between neighboring nodes becomes closer, and it returns applicant vectors. To predict collaboration relationships, a combined vector made up of a pair of co-applicants is needed, not a single node vector. Here, the relation operators in table 1 are used to generate a relationship vector between node pairs. In this step, MMR is applied based on the co-applicant vectors generated through node embedding to explore potential R&D collaboration partners. MMR can consider both semantic similarity and diversity at the same time. At this point, vectors that are different from the already selected relationships but still have high similarity are chosen. Similarity is measured based on cosine similarity. Potential and the collaboration partners are defined based on the new rings selected by MMR. These results are likely to be organizations that are not existing business partners. This study proposed a method that applies node embedding and MMR to a co-applicant graph to identify potential R&D collaboration partners. Based on this, experiments were conducted, and the process consists of data collection, co-applicant embedding, and potential co-applicant exploration. First, patent data related to autonomous driving technology were collected in this study. In this step, patent data filed in 5 countries were collected. A co-applicant graph was built based on the collected patent data. The node size represents the number of connected links, and the color indicates the country of application. The applicant abbreviations represent research institutes and universities, respectively. Node-to-back was applied to the co-applicant graph to perform node embedding. The detailed parameters related to this are represented in the table 2. Vectors derived earlier were reduced in dimension and visualized. The node shape represents the type of applicant, and the background indicates the country. This shows that the nationality and neighbor relationships of the applicants are also well reflected in the vector space. The hyperparameters were optimized based on ring prediction. GM and AUC were compared according to different combinations of node-to-back hyperparameters to optimize the return parameter and the inner parameter. In addition, by comparing operators and prediction models, it was found that weighted R2-based KNN showed the most balanced performance. Pairs with a high possibility of connection, even so no actual ring exists, were defined and extracted as candidate co-applicants. Based on this, the candidate co-applicants shown in table 4 were derived. The candidate co-applicant graph was visualized. In Japan, the collaboration structure tends to be centered around Fujitsu, while in South Korea, a collaboration network structure centered on research institutes and universities is observed. most potential collaboration relationships tend to be formed within the same nationality. However, there are also cases of companies that show the possibility of multinational collaboration. They propose a method to identify potential R&D collaboration partners for the development of organizations. First, the relationships between applicants who hold patents are represented as a knowledge graph. Next, the applicant nodes are embedded into a vector space. Based on this, the MMR algorithm is applied to identify potential R&D collaboration partners. As a research contribution, this study quantitatively measured collaboration similarity and clarified the procedure for identifying potential R&D collaboration partners. In addition, the proposed method can be widely applied regardless of the technology field or type of organization. This study has a limitation in that it did not consider the relationships between organizations when identifying potential R&D collaboration partners. Since collaboration should consider relationships between countries or competitive relationships, these factors need to be considered in the future. In addition, there is a limitation in that the study did not provide a method for determining hyperparameters, such as the number of node dimensions. Future research needs an improved method that reflects this point. Thank you for listening.